So closing on the discussion of fully connected network architectures, we would like to discuss a bit about this kind of regularization approaches that we have in our disposal. Evidently, one of the regularization approaches we already have seen during the discussion of linear regression, and this was called weight decay, and it was covered back then with the so-called L2, calculating the norm squared of the weight vector and adding it as a penalty factor via a hyperparameter lambda in the mean square error loss. And we can actually go back to our network over here that we have seen, the multi-class classification network, and see exactly how this will apply over here. Going back to this example, we have all the trainable parameters such as the matrix W1, the matrix W2, and so on. They can actually be extracted out of this kind of network, and they can be led into a parallel kind of branch that is actually also shown over here in your site to calculate the terms that are need to be summed up and act as a penalty factor for overfitting. Okay, to avoid overfitting, to drive, if you like, the parameters in a way that they are kind of overfitting can be avoided. So if I can draw a little bit this kind of situation that we have here with weight decay as applied now to neural networks, what I would draw is I would draw the network. I'm not going to draw in its everything we have drawn earlier. So we have this X. We have a network which is consists, if you like, of multiple layers. Let's call this layer W1. In this another layer W2 involving evidently dense matrices, as we have seen earlier. And then here we have a Y hat. We have a categorical cross entropy loss function with a Y. And this is my scalar L. And let me call it LCE. And over here, then what this regularizer is going to be doing, for exactly the same reasons that we have seen earlier, is going to calculate the element-wise I, j squared elements of all the matrix W1, and is going to sum over all I and j to produce a scalar penalty that it is going to sum to the other. So if I may draw like something like this, maybe over here. Just to be able to see exactly the same thing for the matrix 2. So we're calculating the squared values of the matrices of each element of the matrix as an element-wise calculation. We are summing all the squared elements over now I, j again, and we are adding this, and of course we need a hyperparameter lambda that we will weigh the penalty factor against the unregularized cross entropy loss that we are going to sum to our L total. So this is L reg, and of course L is going to be L cross entropy plus L regularizing. So this is effectively the exactly the same equation, so as we have seen earlier, and exactly the same method. We should expect to see exactly the same kind of behavior and rationale as to why we are actually doing that. So we are not going to be cover that in any more detail. What I'm going to, however, cover is another approach that is also available for us, and this approach is actually called dropout. So in the dropout approach, is actually a very popular approach. We are effectively switching off selected neurons in our original kind of network. So we have the original fully connected, let's say, network architecture. And as you can actually hear, probabilistically, we are switching off some of the neurons. So effectively, we are forming a multiplicity of neural networks during training. And what we are effectively trying to do that is to sort of average over many behaviors of neurons, of this kind of networks that we are sampling. It has been shown that this kind of dropout technique is, and it's actually called dropout because we are dropping certain neurons in favor of the others. And has been shown that this actually has quite good regularization kind of behaviors. Effectively, the way to intuitively understand it is that we are kind of switching off a portion of our total number of parameters by dropping off these neurons, and we're doing it however, in a probabilistic way. Not exactly these neurons are switched off during the whole training process, but there is a probability that we are using, probability distribution we're actually using to turn them off. Okay, so that is basically the dropout, and it's actually better to experience it in an actual implementation, and we'll have a chance to do that in another exercise in this course. And then, of course, we have the final approach that we are going to be covering tonight is called early stopping. And in that approach, we are switching, we are stopping the training process the moment we see the validation loss sort of increasing as compared to the training loss. So the moment we actually see that the network is being led to some form of overfitting, as we have seen in an earlier kind of video, it is the difference between validation and training loss that we should be watching for overfitting, then we stop the training process. Okay, so these are the two additional regularization approaches that we have in neural networks